Okay, welcome back. Happy Monday. Today is March the 14th. Today is a very special day, mathematically speaking. Today is Pi Day. Oliver, why is today Pi Day? 314, right? 3.14, 314. So this goes without saying, but when you get home later today, celebrate responsibly, right? It's just people can get carried away when they celebrate Pi Day. So just be responsible. Today we're going to cover integer exponents. We are in the throes of a massive section on exponents and radicals. And we're going to start on page 119. Nothing really coming up in the near future. Our next quest isn't until April 4th, which is like well after spring break. So just doing lots of stuff before our next quest. And we'll begin at the top of 119 with the daily summary. In this lesson, we tackle negative exponents, scientific notation, and roots. Number one, let's look at the pattern after filling in the right-hand column to discover why any number raised to the zero is 1 and what is meant by negative exponents. So you remember last class we defined, oh yes, Haley? Yeah, just give me a minute. Okay. You recall that last class we defined any number to the zero to be 1, right? Anything to the zero we said is equal to 1. Emma asked why is it true? I said hold off until Monday. And so now we're going to figure out why that's a reasonable definition. Any number to the zero is 1. Let's take a look at the right-hand column. And we're going to start right here. 3 to the first is 3. And we're going to go up the ladder in the beginning here. 3 squared is 9. 3 cubed, 27. And 3 to the 4, 81. Okay, so all stuff we know. Go ahead and fill those in. The rule for walking up the ladder is multiply by 3. If you take a look at every number, you multiply by 3, and that gets you the next number up the ladder. Yes? So if the rule for going up the ladder is multiply by 3, then the rule for going down the ladder is divide by 3. Yes? So 81 divided by 3 gives 27. 27 divided by 3 gives 9. 9 divided by 3 gives 3. What should I put in this next spot right here? A 1. Because the rule is just divide the previous number by 3. That's 1. This is why we define any number to the 0 to be 1, is because the definition of exponents is basically just multiply by the base over and over again. So if we're going the other direction, dividing by the base, we're going to get 1 no matter what that base is. And it wasn't special that it was a 3. Could have been any number. Always put a 1 there. Another reason to define any number to the 0 to be 1, suppose that I gave you this, x to the 4 over x to the 6th. Remember, we've got a shortcut for this guy. What do we do with those powers? We subtract. And in this case, we'll have x squared left over, but where will the x squared be? On the bottom, because there's more x's down there, right? So x squared downstairs. What invisible number do we need to bring in here? And have a 1 as a placeholder. Okay, so that's fine. That's old. Suppose that I had this, x to the 5 over x to the 5. We know what the answer is. For sure, this is equal to 1, right? I mean, it's definitely 1. But what if I do my subtraction property? What do I get? X to the 0, right? You subtract 5 minus 5 and you get 0. So if I'm going to define x to the 0 to be something, what do I have to make it? I have to define it to be 1, right? If I want that subtraction property to work, and I sure do, any number to the 0 needs to be defined to be 1. Okay, so that's the justification for why anything to the 0 is 1, but let's keep going down this column. We know the rule for going down the column is divide by 3. So let's just go down and divide by 3. So 1 divided by 3, we just write it, 1/3. And if we take that guy and divide it by 3, now it gets a tiny bit trickier. We'll just do one example out and then the pattern should be clear. I'm taking 1/3 and dividing by 3. Yeah, it is. You guys remember divide you can change to multiply by the reciprocal? Remember that? Right, keep the first, change the division to multiplication, and flip the second. And then multiplying fractions, you go straight across, right? So 1/9. and then divide by 3 again. What do we get? 1 over 27, and divide by 3 again, 1 over 81, right? And so if we're going to define these negative exponents to be anything, I think we got to define them as they are in the table. And so for example, if we just focus on one of these rows, say this one right here, 9 happens to be the same as 3 squared. So 3 to the negative 2 is the same as 1 over 3 squared, 1 over 9, right? I mean, like we agree that 3 to the negative 2 had better mean 1 over 9. So a shortcut, if you don't want to have to make the table every time you say 3 to the negative 2, is just say, hey, 1/9 is really just 1 over 3 squared. And so our basic definition, if you see a negative exponent, you're just going to move that whole thing to the bottom of a fraction and make it a positive exponent. That's what it turns out to be. It's just 1 over. Every negative exponent is just a 1 over. Okay, so that's our basic rule right here. X to the negative n is just 1 over x to the positive n. That generalizes this 3 squared business. Likewise, if you have a negative exponent but it's sitting in the bottom, you can just move it up to the top. Doing 1 over has the same effect as moving the thing upstairs. And so I've got this little shortcut in my mind that just indicates that a negative exponent represents movement. If you see a negative exponent in a numerator, you're going to move the whole thing to the denominator and make it a positive exponent. And if you see a negative exponent in the denominator, you're going to make the whole thing a positive exponent up in the numerator. So we're going to try this example in number 3, but it's already written out there, and I want us to feel like we're doing something. So can you just copy that thing from number 3 and some blank space on the next page? I put it down here below the answer key. Just copy that guy. Okay, so we've got negative exponents floating all over the place. Only thing I know about negative exponents is that they mean movement. Okay, first thing I'm going to do is deal with the parentheses. I've got a shortcut. What do I do with the powers when I see this particular pattern? We multiply those, right? That's our shortcut from last class. I'm copying everything else except for that parentheses. So I've said this before, but a lot of math is about copying everything and making one small change. So the one small change is e to what power when I multiply? -6. Okay, so that's the only change. Now those parentheses end up multiplying those exponents. Okay, so now we've got negative exponents floating all over the place. Instead of being intimidated by them, we just recognize this one little shortcut. Negative exponents indicate movement. So let's start on the top. R to the -9. It has a negative exponent. That means move. So we take that R to the -9. We put it downstairs as R to the +9. That's it. That's what the negative exponent means. It means move it. If it was in the top, like the R to the -9, you move it to the bottom, make it R to the +9. That's all. Very tempting to take that 5 and say, oh, it moves. Don't copy that because it's wrong. 5 has no reason to move. It's the negative exponent that indicates movement, and that exponent of -9 is not touching the 5. Remember, exponents are a lot weaker than we might give them credit for. The 5 has no reason to move. It does not have a negative exponent on it. It stays right where it is. Going downstairs, there was a 25. Does it move or stay? Stays. 25 there. R to the -5. Move or stay? Move, and it moves up. It was down. It moves up and becomes R to the 5th. That's all you do. You see a negative exponent, you move it, and you make it a positive exponent. That's it. E to the 8. Move or stay? stays. It's positive. It has no reason to move. It's the negativity of the exponent that tells us to move. But if an exponent is positive, it don't do anything. You wouldn't have done anything before 2 minutes ago when we learned about this motion thing. And finally, d to the -6, move or stay. Move upstairs and becomes d to the 6. Good. And now in its current form, this is a problem that I could have given you on Friday's class to do, because we've gotten rid of all the negative exponents. So the key for today, see a negative exponent, move it, and make it positive. So let's finish up. I'll make a blank fraction line here. 5 and 25 reduced to 1 and 5. I'll leave the 1 missing for right now. What do we do with the exponents on the r's? We subtract. That's our familiar rule. So there's 4 left over where? On the bottom, because that's where there were more of them. R to the 4. Same property on the d's. We're subtracting. So there's 2 d's left over where? On the bottom. D squared. Turns out there isn't anything left over to write on the top, so I, again, need to bring in my invisible placeholder, which is 1. So that's the answer. 1 over 5 r to the 4 d squared. We didn't really read the directions carefully on this one, but it said make all the exponents positive. That's what we've accomplished. We had lots of negative exponents, lots of things that could get combined. We had, 2 r terms and 2 d terms, and now we smushed them all together to a single r term, single d term with only positive exponents. Any questions on that example? Okay, just a quick aside here. Suppose that I give you this, 2 to the -3. Definition of this, it's got a negative exponent, so I move it. Where do I move it? At the bottom. I mean, if you want, you can put the invisible over 1 in there so you can see it's part of a fraction now. So we move it to the bottom, make it 2 to the 3rd. And a 1 over up there, right? And so this is just 1 over 8. But you'd be surprised the variety of answers when I give problems like 2 to the -3 without a calculator. People will tell me it's like -8. Like they think that the negative exponent just makes the final answer negative. It doesn't. If it did that, I would have just put a negative in the front of the thing in the beginning. Negative exponents have nothing to do with negative numbers. Negative exponents have to do with motion. Okay. It turns out that there actually is a shorter way to do this problem. That shorter way wouldn't have given us all this good practice with negative exponents and moving, but I'll just show you. Here, we do have a property that says do what with those exponents? We add those exponents, right? That was the first property we talked about the other day. You add those exponents, and what do you get when you add those exponents? 8 plus -6. 2. D to the 2. 8 plus -6. So we didn't need to actually move that d to the -6 upstairs, although of course we'll get the right answer by doing that. I wanted us to practice with this movement idea, but it's not to say there's only one way to tackle these problems. And with these exponent problems, there's often several ways to do it. This one's even tougher, but that guy right there, what do you do with those powers? Subtract them. Like, doesn't matter that they're negative numbers. We know we're supposed to subtract. Division becomes subtract the powers. Okay, so you get to subtract. Now you can subtract in either order you want. We're really hoping to get a positive answer at the end of the day. Do you want to do the top number minus the bottom number, or the bottom minus the top to get a positive answer? I want to do the bottom minus the top. We always do the bigger one minus the smaller one, right? Where are there more? The bigger one is this -5, even though it's negative. So if you do the bottom minus the top, -5 minus -9, that becomes -5 plus 9, which is really 4, which means r to the 4 is going to be in your answer. And we said there were more r's in the bottom, so that's where the r to the 4 will end up. And it's here. Not saying you have to do it that way, but that is a shorter way to do it. For now, I want us to practice with this negative exponents meaning movement idea. Okay, so I think that was it for this page. Let's do one last thing on the top of this page, number 4. Scientific notation allows us to easily work with very large or very small numbers. We write numbers in this format by writing a number between 1 and 10 multiplied by a power of 10. So let's see what that means. On this particular date and time, the US national debt was approximately that many dollars. We're going to rewrite this number using scientific notation. First, let's see if we can just figure out the name of this number. This right here is the hundreds group. What's the next group? So thousands is that whole collection of 3. Millions is the next one after that. Billions, and then finally trillions. So that's 15,460,000,000,000 dollars. Right? That was the national debt at that time. It's undoubtedly larger now. But it's kind of annoying to figure out what that number is. Like, you literally have to count the placeholders to figure out that that's the trillions, right? And you can imagine that there might be astronomers dealing with numbers that are many, many more zeros than this one. And so just to make it easier to read, we're going to use a different kind of thing called scientific notation. So here's the idea. We're going to take the decimal place, which is currently here, and we're going to move it someplace. You can move it anywhere you want as long as you pay for it. So for example, if I move it like right here, then that is the number 1,546. Yes? Okay. I have to move it to a place where I get a number between 1 and 10. And 1,546 is too big. It is not between 1 and 10. Suppose that I were to move it here, read that number out loud. 154.6, yes? Is that a number between 1 and 10? No, that's not the winner. Read this number out loud. 15.46, that is close, but it is not between 1 and 10. Read this number out loud. 1.546, is that between 1 and 10? It is. That's the winner. So we're going to take our $15 trillion number. We're going to write it as 1.546. But 15 trillion is not 1.546, so we have to pay for it. So here's how we pay for it. We're going to multiply by 10 to the correct power. How many places did you have to move that decimal point from the start to the finish? We'll vote for 13. Up there, 13. So this is 13 places. And 13 is the thing that goes right up there. Because we know that multiplying by 10 to a power just moves the decimal point that many places over. So because we moved it, we kind of artificially moved it 13, we need to multiply by that 10 to the 13 to put it back where it belongs, to give the reader of that number instructions to say, hey, but really move the decimal place 13 to the right. Okay, so that number right there is in scientific notation. Clearly, you don't need to play the game where you say, okay, 1,546 and 154. You just got it. You can just zip it right to the final answer. The only place we can put it is there, 1.546. Oliver. It's just a convention. Yeah. I mean, the fact is, like, we have a lot of experience with numbers between 1 and 10. You can visualize numbers between 1 and 10. It's hard to picture for example, 1,546 of some things. And so let's put it in a place where we're all comfortable, but also let's standardize it so that everybody in the world is going to put it in that same place. Okay, let's take a look at this guy right here, the part B. The diameter of a typical bacterium is about 0.000000241 meters. We're going to rewrite this number in scientific notation. Okay, same idea as before. You're going to put that decimal place in the one spot that gives you a number between 1 and 10. Between what two digits am I going to put this decimal place? Between the 2 and the 4. You buy that? That's the only spot we can put it, because 2.41 is between 1 and 10. So we start by writing 2.41. 10 to a magic power. Let's count. How many places? 7 is right. I actually made this easier for you to read by doing what? When I typed up the 0.000 number, how did I make it easier for you to read? What's that? It's in groups of 3, right? There's a little space that helps us count because you can't use commas for a number. You can't use commas after a decimal place, right? So like the commas help us up in this number because we know they're all in groups of 3. It's a convention for folks writing a lot of numbers that have a lot of zeros in the front is, hey, let's make it easier on the readers and put a little space between every set of 3. Okay, so we said 7 places it's going over, so 7 there, is that right? It's -7. Yeah, 2.41 times 10 to the 7 would say move the decimal place 7 to the right, but we need to tell the reader, hey, you got to move it 7 places to the left. And just kind of logically makes sense. Hey, if going to the right is a positive exponent, then going to the left is a negative exponent. But even if it's not clear to you, well, hey, look, 10 to the -7 is something we defined today. So we're just going to do this over here. 10 to the -7 really means 1 over 10 to the 7. And so that 10 to the -7 is really saying, hey, divide by 10 to the 7. And that's exactly what we want to tell the reader to do. Dividing by 10 to a power moves the decimal place to the left, that power. Okay, and both of those are in scientific notation now, a lot easier to read, and scientists much prefer these numbers to be written in that way. Takes up less space, easier to read, easier to write, easier across the board. Any questions on scientific notation? Oliver. You actually don't even need parentheses around it, but you could to really make it clear to you, hey, this is the single number. But yeah, I don't think it needs parentheses. Okay, on the next page, you will find the first of several activities. So you're just going to do one and then move to the next one. I will walk around.